discussed about conventional MPI radar, which is not the most typical one in practical usage. So, in this class, we are going to discuss about the MPI radar with power amplifier transmitter and the MPI radar with power oscillator transmitter. Along with that, we are going to discuss delay line cancellers, okay, which improve the frequency response of the received echo signals by excluding clutter. So here, based on the design available in the MPI radar, okay, in modern usage, so the MPI radars are classified into two types. So those are MPI radar with power amplifier transmitter and MPI radar with power oscillator transmitter. So in the previous design, we had seen MPI radar uses two antennas for doing transmission and reception. Whereas in these modern MPI radars, so both actions, the transmission and reception, can be done by using single design block, which is known as duplexer. So here, in both two types of MPI radars, so those are MPI radar with power amplifier transmitter and MPI radar with power oscillator transmitter. So both use a single antenna for the transmission and reception of the signals, so which can be done with the help of duplexer. So now in the next slide, we are going to see the block diagram of MPI radar with power amplifier transmitter. So this is the block diagram with the transmitter section contains power amplifier. If the transmitter section contains power oscillator, then it is known as MPI radar with power oscillator transmitter. Understood? And what was the difference between the conventional MPI radar and this MPI radar with power amplifier? So the most significant difference lies in the reference signal. Okay, so how the reference signal is supplied to the phase detector. So if you look at the conventional MPI pulse Doppler radar, which we have discussed in the earlier section, so this is the MPI pulse Doppler radar which we discussed earlier. So it contains simply a pulse modulator, continuous wave oscillator, power amplifier in the transmitter section, so which is transmitted using one antenna, and another antenna is used for receiving the echoed signal from the moving targets, and it is fed to the receiver. So along with from transmitter section, the reference signal is obtained from continuous wave oscillator. Okay, so whereas if you look at this design, so here the reference signal is obtained from the coherent stable oscillator, which is denoted by FOFO. So the main difference lies how the reference signal is supplied to the phase detector, which is available in the receiver section. Now coming to the operation of this MPI radar with power amplifier. So the operation is same as MPI radar with power oscillator radar. So in the transmitter section, we just use power amplifier, which gives us high power gain. Okay, so the operation, let us discuss the operation block by block. So here if you see, this is a duplexer which acts as the both transmitting and receiving antenna. Okay, so pulse modulator, coming to the pulse modulator. So pulse modulator generates the pulses which can be transmitted with the high power gain available from the power amplifier. See, before transmitting these signals, so how these signals are combined, let us see first. So this is the in the middle, if you see the block which is known as a STALO, which is nothing but the stable local oscillator. So from this we are going to obtain the signal for transmission. So STALO Okay, so stereo generates a signal which is having the frequency FL. Okay, similarly coherent oscillator. Okay, so which is denoted by coho, which is this is also stable oscillator. Okay, so that is why it is known as coherent oscillator. Okay, which is denoted by coho with frequency having FC. So the signal from stereo and the signal from coho are mixed in mixer 1. Okay, so the mixed signal which contains the frequencies FL plus FC are going to be transmitted to the power amplifier. And whenever pulse modulator turns on the power amplifier, the signal can be transmitted. So whenever pulse modulator turns off the power amplifier, then the signal will not be transmitted. Okay, so when the combined signal which is having the frequency FL plus FC is transmitted using the transmitter antenna available in the duplexer, whenever it goes and hits the moving targets, so and the echo signal which is coming back from the moving target is again received by the same antenna, so which is available in the duplexer, and it can be shifted by Doppler frequency. So as we discussed earlier, so the main theme of this MTI radar is nothing but, so whenever the transmitted pulses strike the targets which are moving continuously, and the echo signals which are coming back from the targets are received by the receiver, okay, they will undergo the frequency shift which is equal to the Doppler frequency. So that is why the transmitted signal which has the frequency FL plus FC, okay, so will be received at the receiver as echo signal which undergoes by the Doppler frequency shift FT plus or minus FT. So as I discussed earlier, so this plus or minus is determined by how the target is approaching us. So whether it is approaching towards us, the plus sign should be used. So the received echo signal will contain the frequency which is the combination of FL, FC and FD. Okay, so sum of these three frequencies. So whenever the target is moving away from you, okay, then the receiver echo signal will have the frequency FL plus FC minus FD. Do you understand? So now these two, okay. So the receiver echo signal which has the combination of these three frequencies, and the transmitted signal, okay, the transmitted signal which is generated by scalar, okay. So having the frequency FL, so will be given to the mixer 2. So in mixer 2, the received echo signal and the local oscillator, okay, stable local oscillator, scalar signal are combined together. So what is the use of mixer here? So the mixer is going to generate the either sum or difference of the signals, okay. So the signals which have the same amplitudes, so the echo signals which are nothing but the which are nothing but coming from the fixed targets will be cancelled out. Only the uncancelled value, okay. So the remaining value which is nothing but the received echo signal coming from the moving targets, okay. So will not be cancelled, and this will be the output of the mixer 2. So mixer subtracts most of the amplitudes which are in common, and the amplitudes, okay. So we know that the amplitudes of the non-moving targets are same. The amplitudes of the moving targets will differ. So that is why the output of the mixer 2 is nothing but the signal which is coming from the moving targets, which is of our interest. So this has a frequency which is equal to FC plus or minus FT. Okay, and again what we have discussed earlier, okay. So these two there should not be any phase shift in the signal. So that is why the coherent oscillator will transfer the reference signal of same phase having which same phase of that of echo signal. So the intermediate frequency amplifier amplifies the signal which is received at the receiver. That is nothing but the echo signal from the moving targets. So this coherent oscillator again generates the reference signal. Okay, so whose phase shifts are same. Okay, so in the IF amplifier, the received echo signal will get amplified, and in the phase detector, okay, so where we need only the Doppler shifted frequency signal is of our interest. So here we need to cancel out the carrier frequencies Fc. So that is why Fc plus or minus Fd is given to the phase detector, and from coherent oscillator the reference signal is given to the phase detector. So here the same carrier frequencies Fc will going to be cancelled, and the different signal which is of main interest, which is nothing but the echo signal, which has undergone frequency shift by Doppler frequency, can be obtained, and this will be given to the yellow line canceller for further improvement. So previously we have discussed the MPR era with power amplifier transmitter. So before these power amplifier transmitters were invented, so there were only magnetron oscillators which provide the high power. So in case of MPR era with power oscillator transmitter, we are going to use in the transmitter section magnetron oscillator instead of power amplifier. Okay. So these were the designs which are available before the invention of power amplifiers. Okay. So magnetron oscillator can give us high power, so that these can be used in the MPR eras with power oscillator transmitter in the transmitter section. So the operation of the MPR era with power oscillator transmitter is same as to that of MPR era with power amplifier transmitter, but the only thing is, instead of power amplifier we are going to use magnetron oscillator. So this magnetron oscillator, okay, frequency will be locked with the intermediate frequency which is available in the receiver section, and the same locked frequency is applied to the phase detector, okay, to obtain the Doppler shifted frequency signal at the end. Okay, so if we look at the operation of this MPR era with power oscillator transmitter, and let us start with the local oscillator. Local oscillator generates a signal which is going to be transmitted, and coherent oscillator, okay, so we'll generate the signal to the reference as the reference to the phase detector. Okay, so local oscillator generates the signal to the mixer 1, and magnetron oscillator also generates the signal to the mixer 1. Okay, so magnetron oscillator, it has the frequency the same as to that of intermediate frequency which is available in the receiver section. So FL and this value will be combined here. Okay, in the the output of the magnetron oscillator and the output of local oscillator will be combined in the mixer 1. Okay, so which is nothing but the FC plus or minus FL. Okay, so whenever pulse modulator turns on the magnetron oscillator, the signal can be transmitted using the duplexer. Okay, and whenever pulse modulator turns off the magnetron oscillator, there is no transmission from the magnetron oscillator. So at the duplexer, since the duplexer acts as both transmitting and receiving antenna, so okay, since the duplexer acts as both transmitter and receiver, it contains a single antenna for doing the same purpose. So the received echo signal from the moving target will be received here at the same duplexer. So which is shifted by Doppler frequency. Okay. So here the received echo signal at the duplexer will contain the frequencies FL plus FC plus or minus FD. So that is applied to the mixer 2. And similarly, from local oscillator, the local frequency signal, okay, so which we have transmitted previously, is given to the mixer 2. So here the frequencies which are same are nothing but FL, okay, will going to be cancelled. So the output of mixer 2 is nothing but the FC plus or minus FD, okay. So the phase of these signal will be same as the coherent oscillator signal, okay, and the frequency of intermediate frequency amplifier, the received echo signal which is obtained from the IF amplifier will be same as to the locked pulse of magnetron oscillator and coherent oscillator, okay. So in the phase detector, FC plus or minus FD is going to be combined with the FC, okay. So FC, which is nothing but the carrier frequency. So this carrier frequency is going to be cancelled in the phase detector, and the output of phase detector is nothing but the Doppler shifted received echo signal, which is obtained from the moving targets. So if you see the operation here, the output of magnetron oscillator and output of local oscillator applied to the mixer 1. So this will further produce IF signal, which is in the same phase as to the transmitted signal. So the output of mixer 1 is applied to the coherent oscillator, as we have seen here. Okay, so this is applied to the coherent oscillator, which is locked with the phase of the intermediate frequency signal. So the phase of coherent oscillator output will be directly related to the phase of the transmitted signal. So there is no phase shift change here. So this phase of transmitted signal, received echo signal, and coherent oscillator signal will be same. So the output of coherent oscillator can be used as reference signal for comparing the received echo signal with the corresponding transmitted signal using the phase detector. And after that, the obtained output is given to the delay line canceller. So for further processing. So here, what is the use of delay line canceller? Let us see clearly. So delay line cancellers. So these are nothing but the time domain filters, okay, which introduce a shift in time. Okay. So delay line canceller is a filter which eliminates the DC components of echo signals received from stationary targets and allows only AC components that are obtaining from moving targets or non-stationary targets. So this is very simple. So the advantage of delay line canceller over range gated Doppler filters is that so it can operate at any ranges. Okay, only single network is enough to develop delay line canceller, other than Doppler range gated Doppler filters. So where in range gated Doppler filters we need range gates for several sections. Okay, and for each range gate we have to take another band pass filter as well. So all that complexity will be reduced if we use delay line cancellers. Okay, and based on how many delay lines are available, there are two types of delay line cancellers which we are going to discuss now. So if the delay line canceller is only one, it is known as single delay line canceller. And the delay lines available are two, then it is known as double delay line canceller. So like that, based on how much accuracy we need, so we can increase the number of delay lines. This concept will be extended for n delay line cancellers also. So if you look at the single delay line canceller, So it is just the combination of one delay line and one subtractor. Okay, so it is called single delay line canceller since it contains only single delay line block and in combination with one subtractor. So if you look at here at the receiver, when the receiver antenna receives the echo signal, which is nothing but Doppler frequency shifted echo signal. Okay, so it is just given to the delay line. So the receiver section will be modified into two sections. So one is for allowing only the video signal, which is nothing but the same received echo signal. The another one will be undergone one time delay. Okay, so which is the time delay is equal to the period of the pulse signal. Okay, so time period of the pulse signal, which is given by TP. Okay, and at the subtractor, both can be subtracted. Okay, so the difference can be generated using the subtractor section. Okay, which is nothing but the bipolar video signal. So this bipolar video signal is given to full wave rectifier to obtain only unipolar video signal. And this unipolar video signal is applied to the indicator to detect the moving targets on ASST. Okay, so previously in the conventional continuous wave radars and MPA radars, we had seen the butterfly effect, which is the indication of the moving targets. Okay, the presence of moving targets. So only the butterfly effect is not sufficient enough to detect the moving targets. So that is the reason we have applied delay line canceller concept to distinguish moving targets from fixed targets. So since here we are applying subtractor, okay, so the output will be very clear to detect the moving targets from stationary targets and by separating clutter from the output. So the mathematical equation of the received echo signal after the Doppler effect is nothing but V1. Okay, so which is given as V1 equal to A sin 2 pi FTT minus F0, which is same as the voltage. Okay, so the voltage of conventional MPA radar. So but if we apply delay line canceller, so here this value, okay, this echo signal will be undergone by one period delay. Okay, so that is given by TP. Okay, so TP is nothing but the time period of pulse. Okay, pulse interval. Okay, so the output of delay line canceller by replacing T by TP. Okay, so T minus TP is given as V2. So A sin 2 pi FT T minus TP minus F0. So here T minus TP is nothing but the delay introduced in the echo signal. Okay, when we use single delay line concept. So now these two voltages are fed to subtractor. So the subtractor output, okay, by subtracting V1 and V2 will be given like this. V1 minus V2 equal to, so A sin 2 pi F dt minus F0 minus A sin 2 pi Ft T minus Tp minus F0. So as we know from mathematical expressions, okay, sin of A minus B minus sin of A minus B. Okay, so this can be written as 2A sin Ft Tp cos 2 pi Fd T minus Tp by 2 minus F0. Okay, so this is the output of the subtractor. Okay, this is the output of the subtractor. Okay, so which is obtained by taking the difference of a received echo signal and delay line, single delay line. And here if you see in the difference voltage, okay, so which is obtained after subtraction. So here it contains sin phi FDTP. So this what actually it suggests us. So whenever sine value is integral multiple of pi, the value will be 0. So sine pi is 0, sine 2 pi is 0, sine 3 pi is 0. So like that, whenever the sine value is integer multiple of pi, the voltage is going to be 0. So what does it suggest as? Okay, so whenever the sine value is integer multiple of pi, the total voltage is going to be 0. So which is nothing but the indication of blind speed. Okay, so that concept we'll see here. So this is the output of subtractor which is applied to the as the input to the full wave rectifier. Okay, so after applying that subtractor voltage to the full wave rectifier, so the bipolar video will be converted into single polar video signal. Okay, so which is obtained only in the form of unipolar values. Okay, so this is the graph which is given between amplitude and frequency. So the full wave rectifier output is only unipolar video signal. So as we have discussed earlier, so we can observe that the frequency response of the single delay line canceller becomes 0 when pi FDTP equal to 0. Sorry, is the integral multiples of pi. So because it contains sine, okay, sine value will be 0 when it is integer multiple of pi. So that is why the single delay line canceller becomes 0. Okay, the frequency response of the single delay line canceller becomes 0 when pi FTTP is equal to the integral multiples of pi. So mathematically it can be written as pi FTTP equal to n pi. So where n equal to 1, 2, 3 and so on. Okay. So pi will get cancelled. FTTP equal to n and FD equal to n by Tp. So 1 by Tp is nothing but the pulse frequency. Okay, pulse repetition frequency. So FD equal to n FT. So from this expression, what do we understand? So we can conclude that the frequency response of the single delay line canceller becomes 0 when Doppler frequency is equal to the integer multiples of pulse repetition frequency. Okay, so whenever Doppler frequency that in the received echo signal is equal to the integer multiples of the pulse repetition frequency which we have transmitted. Okay, so when both are same, okay, then there will be 0 frequency response. That means that voltage, okay, so that targets will not seen by the MPI radar. Okay, so which further give us the concept of blind speeds. So the blind speeds are the velocities at which radar is not able to see the moving targets. Okay, so this is the main drawback of MPI radar. Okay, the relative velocities for which frequency response of the single delay line canceller becomes 0 are called blind speeds. Okay, so these are the speeds where the radar is unable to differentiate which is the moving target and which is the fixed target. So it just notice that this will be the clutter and thus it will eliminate that voltage. So that is the disadvantage of MPI radar with delay line cancellers. So the blind speeds will be the effect of or the drawback of MPI radar with delay line cancellers. So these blind speeds, okay, can be written in the form of mathematical equation as Vn equal to n lambda by 2 Tp. Okay, so where n is equal to 1, 2, 3 and so on. Okay, so Vn is nothing but the n velocity. Okay, so of a received echo signal. And lambda is the wavelength of the received echo signal and Fp is the pulse repetition frequency by 2. Okay, so these are the blind speeds, so at which radar is unable to distinguish moving targets from clutter. Okay, clutter is nothing but the received echo signal using receive echo signal from fixed targets. So it will not be able to distinguish between fixed targets and moving targets. So those velocities at which radar is unable to decide which is clutter and which is moving target is known as relative velocity. So is known as blind speed. So here we are going to use two delay lines, which is nothing but the double delay line concept. So to avoid the clutter spectrum in a broad way. Okay. So the frequency response of a single delay line canceller doesn't always have as broad a clutter spectrum null as reside in the vicinity of DC. So actually filter eliminates the DC components and allows only the AC components, which are nothing but the received echo signals from moving targets. But by using single delay line canceller, the clutter rejection is not more accurate as enough for our usage. That is why we are going to use two delay lines to avoid the clutter in efficient way. So the clutter rejection notches may be widened by passing the output of the delay line canceller to a second delay line canceller as shown here. So previously we are able to subtract, or we are able to avoid the clutter spectrum, but it is not as per the wish. Okay, it is not for the but it is not as per the requirement of our criteria. So that is the reason here we are allowing the received echo signal. Okay, so which is obtained from the moving targets. Okay, so along with the clutter we are including one more delay line for the single delay line canceller. So this is the block diagram which shows the two delay lines, which is known as double line canceller. Okay, double delay line canceller. So P of T is the received echo signal, okay, which is passed through delay line once, and same is given to the subtractor. So here Q of T is the output obtained from the subtractor 1, and this Q of T is delayed once more, and this Q of T is applied same to the subtractor 2, and at the subtractor output R of T is the difference voltage, okay, which is given to the phase detector. So the advantage of double delay line canceller is that it rejects the clutter broadly. Okay, so it will eliminate most of the DC components coming to when we compare to the single delay line canceller. Okay, so the output of two delay line cancellers will be equal to the square of the output of the single delay line canceller. So if we increase the number of delay lines, so the output is always square of the input. So the magnitude of the output of double delay line canceller, which is present in ampere radar receiver, will be equal to 4a square sin pi FDTP whole square. So if you see the output of single delay line canceller, so here you can see the difference voltage as 2a sin pi FDTP cos 2 pi FDTP T minus TP by 2. So when we use two delay lines here, so here for sine value we are going to get sine square. Okay, so that is by 4a square sine square pi FDTP whole square. Similarly cos square 2 pi FDT T minus T2 by 2. So the output will be square of the input for each number of delay lines increased. So that is the reason here we will be getting the output as 4a square sin pi FDTP whole square. If we increase n delay lines, okay, so then we will be getting here, okay, so a power n sin pi FDTP whole power n. Okay, so this value will be increasing by square for each increment in delay line section. And if we observe the frequency response using two delay lines, okay, in double delay line canceller, so as like this. So in single delay line canceller, we have seen the output frequency response as like this after applying to the full wave rectifier. Okay, so but here if you observe clearly, we can get broader DC rejection. Okay, so here this is the frequency response versus amplitude. Okay, so here the solid line is indicated, is the indicator of single delay line. Okay, so the solid line represents the frequency response obtaining by using single delay line canceller, whereas the dashed line, okay, represents the frequency response obtained by using delay line, two delay line cancellers. Okay, so double delay line cancellers. So here the broad value, okay, which are denoted by the pulse. Okay, so this is the clutter spectrum. Okay, so if you look at this frequency response clearly, so most of the DC spectrum is going to be eliminated when we increase the delay number of delay lines. So by using single delay line canceller, we could see some of the DC clutter is going to be present in the frequency response. But when we increase the number of delay lines, okay, in the double delay line, okay, so in the double delay line canceller, so this value, okay, is going to be reduced as much as possible. Okay, so that is the reason when we increase the number of delay lines, the clutter rejection will be broadened. Okay, but the only drawback of delay lines is that they introduce blind speeds. Okay, so the blind speeds will not be avoided by using this time domain delay line concept. So that is the reason in the next class we will be going to discuss the frequency filters, okay, so which are nothing but range gated Doppler filters, so which can avoid blind speeds and increase the efficiency of the received signal obtained from moving target.